So we're going to go ahead and get started on circuits here, and this will be our little introductory video where we define a few little things and make sure we know what we're talking about so we have the proper language. The first thing we need to define is a cell. You probably usually call this a battery, but this is a cell. It's basically just a component, electrical component, that gives the electrical energy or electrical potential energy or electrical voltage, but it provides our electrical energy. When we draw these pictures, you just draw a straight line, and that's a wire, and then we connect components with these straight line wires. And so for this particular thing, a cell, you'll get a long line and a short line. The long line, and then of course we have the wire coming out of it. So this represents our cell. This is the positive side, this is the negative side. They aren't always labeled like that, but you know that the longer side is the positive and the shorter side is the negative. Sometimes they're strung together, and just depends on different conventions what it might mean, but usually it's, you can get like several of them strung together, like cells put together to make a battery. Again, positive side, negative side, and basically that's our cell. It has high voltage on this side and low voltage on this side, so if you go across this way from right to left there, it increases your voltage. If you go left to right, it decreases your voltage, and then usually it'll be labeled with something like this could be 8 volts or something, and this could be 1.5 volts. Now, cells as they are produced, they actually really max out at 1.5 volts. They're created chemically. And we'll worry more about that later, but that's the maximum they can do is 1.5. You create batteries by chaining together multiple cells, and then you can increase up this voltage. It'll add up. So a 9-volt battery would be 6 cells, so 6 1.5-volt cells giving you that 9 volts. All right, the next thing we have to worry about is something called resistance. And this is pretty simple. It kind of defines itself. It's just the resistance to electricity flowing through something. And as far as circuits go, we can usually define it through components with something called Ohm's law. And it's that the voltage through the component, the voltage drop across the component is equal to the current through it times the resistance. That's that resistance of your component. So think of when we're doing these circuits as these wires. They are like guides for electric fields, and so as electric fields flow through them, there's a voltage that drops through the wires. Now the wires are so good at carrying electric fields that we usually ignore the resistance inside the wire, but when you get to different components like batteries and things like that, it can, or what are called ohmic devices, these ohmic devices will follow Ohm's law, and non-ohmic devices don't follow it, and you kind of can only use this like as an instantaneous voltage measurement. And so if we were to graph voltage versus current, you would see V and I. Ohmic devices are going to be linear, they're going to be nice straight lines. Non-ohmic devices are going to be ones where it doesn't stay straight, like maybe it curves, and then you might be able to say, well, it's ohmic, good approximation, it's ohmic in here, but later it curves up and it's not ohmic anymore. So this is ohmic, this is non-ohmic as it's called, and that's just resistance. You apply this to it, and it just tells you can figure how much current is going through it and all that kind of stuff. The unit for this is called the ohm. The unit for resistance, so the resistance unit is an ohm. And if you look at this, you can see it's a volt per amp. Well, we haven't defined the unit for that. It's current, and it's defined as the ampere. Actually, we did in that last video, didn't we? It's an amp. I forgot we had already done that. So we did define that. It has a current of a unit of an amp. Volt has a unit of a volt, and so an ohm is going to equal a volt per amp. All right, and you can break that down further if you want. This is a joule per coulomb. This is a coulomb per second, and you can start canceling out the coulombs and stuff like that. But it's mostly a volt per amp. So ohms amps, volts, okay? And that goes with there. Now the next thing is called resistivity. And this is more of a material property that tells you how good of a how well something or how poorly something conducts electricity. And it's essentially we use the you use the Greek letter rho for it, and it's defined basically as it's your resistance, this resistance per unit length, and times an area, really, the cross-sectional area. And I'll show you this in a second. So basically we can write this as what are the things that would affect how much resistance something has? So if we look at like a wire, say this is our wire here, a cool little angle of a wire. The first thing is going to affect it is how long is the wire. The length of this wire. Does it have to just go through a centimeters worth of wire or 5 miles worth of wire? And that's going to make a big difference. It's kind of like if I told you had to drive through a big mud pit. Well, how much resistance that mud pit's going to offer you going through it and driving through it depends on how big the mud pit is. Is it a foot wide or is it 100 feet wide? That's going to make a big difference. So that's the first thing. The second thing is then how big is this? So if you think in terms of like a pipe, and I was asking you how much water could flow through a pipe, the bigger round, like the larger the diameter of the pipe, the more that can flow through there. The smaller the pipe, the less it can flow there. So what we're going to base this on is the surface area of this cross-sectional area, right? That little part there, the area of it, of that cross-sectional area, how big around is it? And then of course, what is this made out of? And that's the resistivity. Is this made out of copper, in which case it's got a low resistivity and it's a very good conductor, or is it made out of plastic? Then it's going to have a huge resistivity. So this resistivity is basically a material property. All right? And I prefer to think of this as this resistivity, like we were just talking about here, it has some resistivity to it. That determines the overall resistance. And so the higher the resistivity, the higher the resistance. The longer the material, the more the resistance. So it's going to be directly proportional to the length. And then it's inversely proportional to the area, because the bigger that area gets, the less resistance you're going to have. Just like if you have a bigger pipe, more water can get through it. If a bigger diameter wire, a larger wire, more electricity can go through it, and so it's going to be less resistance. They can spread out and get themselves all through it, not cram up all in there. So this is the way I think of the equation, because overall these are properties of your object that tell you what its overall property is. But in your data booklet, you're going to be given it in this form. R A over L. They just isolate the resistivity and define it as that rather than the resistance. I prefer this way. So even if I was given that, I'd probably quickly rewrite it this way so that I can think the way I think about it, just like how I just walked y'all through how I came up with the equation, just by kind of hand wavy looking at the properties of it. Okay, but that's it. This is the one you're going to get in your data booklet. This is the one I prefer to use. Okay, for this resistance, it has temperature has an effect on this. So one of the things that happens typically is in a metal, the hotter the metal gets, oops, I meant to write versus temperature and then talk about a metal versus temperature, is that for metals, these are inversely proportional to each other. So high temperature, not inversely, they're proportional to each other. So a high temperature means a higher resistance or resistivity to it. The resistance goes up. If you think about the little model we talked about before with flowing through electrons trying to get through a material, right? It's made up of a whole bunch of nuclei. As the electrons try to come through, they bounce all around. Well, you can imagine if these nuclei are really hot and they're just shaking around all over the place and bouncing around. I mean, they're bouncing around all randomly is what I'm trying to do there. That the electrons are going to have a much harder time making it through this metal. They're going to get bounced around a lot, and it's going to slow down the overall progress of the electrons to the material. They're going to have a harder time getting through because they're getting knocked around rather than just lightly bumped around by the stationary atoms. And so the resistance is going to go up for metals. You cool a metal off, and the resistance goes down. Now, it's different for semiconductors. These are the things that conduct. They can either act like a conductor or act like a insulator. Semiconductors, a higher temperature means a lower resistance. The same argument works for the semiconductor with electrons trying to go through, but the difference is in semiconductors and non-conductors, the electrons are not free. So if you raise up the energy, it becomes easier to actually strip away those valence electrons because they don't have that whole band gap thing. Becomes easier to strip them off, and so it becomes easier to conduct electricity at higher temperature for those guys. Now, the last thing I want to talk about in this video is electrical power. All right, and then we're going to move on to the next video, and it's P equals VI. Capital P, all this stuff. This is electrical power. It has the same units as before with power. The units are still simply just a watt, a joule per second, but here you can see it's a volt per, or a volt times current. Well, if you remember, it's a volt times an amp. A volt is a joule per coulomb, and an amp is a coulomb per second, and so the coulombs cancel and you're left with a joule per second, and that is a watt. That's a joule per second, it is a watt. So this is our equation for power flowing through a circuit. This works really, really well, and you're going to use it a lot with Ohm's law, with V equals IR. You can combine them together and get different versions. So like if I say V is IR, I can take the power equation, right, combine them together and get P equals, instead of V, I have I times R times I, so that's an I squared R. Or you could substitute out for I, so if I solve Ohm's law, I've got I equals V over R, and I can sub this in and I get that power equals V squared over R. And then the last thing, I think that's where you can just, substitute it in and out and get different little versions. And these are perfectly valid combinations of Ohm's law and our power equation here. The last thing about this power is there's a new unit that comes up other than the watts for it, and it's called the kilowatt hour. And so this isn't really a unit for power, it's a unit of energy. Okay, this is a new unit of energy. If you think about this, well, kilo we can ignore, but it's a watt times an hour. And look, a watt is a joule per second. So this is an energy per time times a time. And so it gives you the total energy in something. And so power companies will use this. They'll tell you they charge you like $2 or something like that per kilowatt hour. And that's just a form of energy. You can convert this to joules if you want, or just use it while it's in that form. It's pretty easy. But you may get a problem where it asks you to solve something like a 50-watt light bulb is run for 50-watt light bulb is run for 24 hours. If it costs $2 per kilowatt hour, how much did it cost to run that light bulb for 24 hours? So you could get a question like that, and you've just got to keep in mind it's $2 per energy. You'd have to figure out how much actual energy you would use up in a 50-watt light bulb in 24 hours, and just make sure your units match up. This is in watts. You'd want to convert it to kilowatts, and you multiply it by how many hours you have, and you'd have the number of kilowatt hours you used up, and then for every one of those you'd have to multiply it by that too, and you'd end up getting it. So like this 50 watts is what, 50 times 10 to the negative third kilowatts, and then you'd multiply that by the 24 hours, and then you would take that and say, all right, now this is a kilowatt hour, this is $2 per kilowatt hour, so your total cost is going to be the amount of energy you use times the rate. That would be something like $2 per kilowatt hour. And you can see the kilowatts and the hours are going to cancel, and you'll end up getting it. So this is your rate, and this is your amount. This two things here, this is the amount you used. So rate times amount, and that's your total. Okay, so just problems like that. Just be used to that being a unit of energy. All right, I think that's pretty much everything for our little introduction, just going quickly over some terms and a few little equations. And now we're going to go on to the next video. All right, that's it.